much. Thank you very much for the invitation to present. I'm going to share my screen now. Okay, so I think it's this one. Okay, can you see my slides now? And then, I hope so. Okay. So I'm going to present quickly. So the topic of my talk today is about AI-powered graphics and animation. So I'm a researcher and lecturer in computer graphics, game, and digital arts, but mainly my focus is on developing computational models or programming for animation and graphics. Hopefully, I'm lucky to have in my office a deep learning machine. So it's a tabletop machine with 5 graphic cards, 5 GPUs for just one user. So it's a workstation. And then, so it means that we have now the computational power to have deep learning in our workstation as individual and not just share fancy deep learning machine like let's say DGX or other powerful machines. So it's can be for the individual. So in computer graphics, we have different problem to solve than classical AI, I would say, because it's mainly based on the nature of the data we have to deal with. So in computer graphics, we deal with images, 3D meshes, and other type of more complex graph-based data. So it means that we can't use classical methods, let's say like CNN or classical methods, because the nature of the data is not Euclidean. So we have to mainly use graph-based approach. So it means that we have to rethink deep learning and adapt the algorithm for deep learning to handle the data we have that is mainly 3D models or animations or 4D models, if you want. In our field, we have very successful methods. So in the scope of geometric deep learning, so we have to use, of course, graph-based methods, so graph neural networks, a generative adversarial network to generate content. And then more recently, we have seen our field a lot of interest for NeRF, so neural radiance field and stable diffusion. So what I'm going to do in this talk is not to present my work, but to present the state of the art. I think some methods, some papers, and what I want to do is not to dive into the details because I have no time for this. You will find the reference of the paper, but you will see the title of the slide and the representative image and the reference paper if you want later to have a look to the methods. But I'm not going to dive into the methods in details because I have no time. So I like this method, this paper that is quite new. So the idea is to have a promptable 3D editing techniques. So the idea is not to ask the artist to use this kind of 3D user interface to manipulate the content or edit the content, but the idea is to use prompts, so mainly text, to drive the process. So we start from a given 3D model, and the user will input some text to guide the process. Let's say, for instance, replace the chicken by a cat in this model, and the system will output a 3D model that will replace the chicken by the cat in the model we have provided. So it's a promptable method. So this is just for one mesh. We have also in the literature some very interesting methods named deep mesh creation. So the idea is to create a mesh with textures. And this time, so we don't really provide a prompt, but what the authors are suggesting is to use reinforcement learning. So the idea of the reinforcement learning is to learn by example, by demonstration. So the user will demonstrate a task in mesh modeling, and the system will learn by training, will learn by demonstration how to create the 3D models. It's just some different techniques. This paper is quite interesting as well because the idea is to focus the method for a very specific type of content that is generating 3D faces. It's a very difficult task because faces are generally small scale details. Let's say like the nose, the eyes, and small facial expressions. So it's very, very small scale detail that has to be generated. And then what this paper is proposing is to use some priors to guide the system. And so the system still need to have some let's say some proxy, let's say like morphable face models, but they adapt the content and they generate new faces with desired facial expressions, emotion, based on the input of the user. And once again, the process is based on neural networks. Now we also have seen in the, so everything we have seen before is for static meshes. So there's no deformation, it's just generating the mesh in a static way. Obviously in animation, the mesh will be animated, so the mesh will be deformed. So namely the surface of the object will be deformed. So we have to find a way to deform the model for animation. And that's why deep learning is also interesting, because the idea will be to use a skeleton to deform the mesh. So this is classical rigging and skinning techniques. But the idea is to achieve this task using skeletal-based deformation, and the deformation of the surface will be learned based on the deformation of the skeleton. And once again, the idea is to have complex deformation and to reduce the amount of tasks that an artist will have to do. This is very task demanding. So the idea is to skip the task to focus on more details or application. There's another paper also that is quite interesting called Neural Blend Shapes. And the idea is to learn the deformation of the skin, once again, based on the deformation of the skeleton. But for this paper, they will use zero-shot generalization. So the idea is that it's possible to generate animation that are not pre-learned during the training. And so that's a difficult task indeed in computer graphics. When we move away from images, is that we have less and less content as data set. And the deformation is difficult. It can be difficult to have this deformation in the training data set. So because we are limited in the training data set, because of the nature of the data, then we have to use a technique that have no supervision. So let's say zero-shot learning. So the idea is to be able to generate content using deep learning without any prior assumption on the data we are going to use to train. Because once again, deep learning is very biased on the data that is used for training. And the idea is to get rid of the difficulty of having good training data set to generate content, especially for animation, so 4D animation. There's another paper also quite recent, quite new, especially published in computer vision, so CVPR this year. And the idea is to use motion diffusion. So diffusion is also very classical and well-known techniques now for generative AI. And the idea is to use diffusion, not just for the shape, but also for the motion of the surface. So once again, the idea is to generate animated models, so with the deformation, and this paper is using motion diffusion to learn the velocity, the deformation of the surface, as far as I have understood the content. And once again, the idea is not to output a static model, but to output a model that is animated, so that have a space-time deformation. That is a difficult problem. Related to all the issues I mentioned before, based on the dataset you use for the training, more and more methods now in computer graphics focus on zero-shot learning. So the idea is to generate content without relying on almost no, or let's say no training dataset. So the idea is that it has two main benefits. Is that we're not limited by the training dataset. We can generate content away from the training dataset. And it's also possible to generate content that is not seen as part of the training dataset. So it's it's a very good direction in computer graphics, zero-shot learning, because we are not limited by the training dataset that has to be generated, synthesized, and or even clean or pre-processed. That is a lot of work and generally limits the learning process. Also, another difficulty is when we want to generate a complex deformation, let's say in performance capture, so a very highly realistic deformation of human bodies to create human performances in full body clothing. It's a very, very complex problem in the past. And the idea is to use deep learning to be able to generate hyper-realistic deformation for the skin, the body pose, and as well as the let's say clothing. So it's a very complex problem as well. And generally, the idea is to do this kind of things starting with just one image, because generally the problem is previous method use a multi-view setup. But if the camera are not well calibrated, or if there's a limited amount of cameras, or if some section of the volume space is not seen by cameras, we have some problem with the incomplete data. So the idea is to use neural methods, especially with the Gaussian techniques, to recreate content, to generate content without away from the noise and away from missing incomplete data that can be observed from the images. This is probably one of the last paper I will, because I don't have a lot of time, is Gaussian surfaces. So obviously, when we have to recreate an animation from, let's say, captured data, let's say images or videos, there's a lot of issues related to noise and incomplete data by reconstruction. So the idea in this paper is to use Gaussian surfaces. So namely 3D Gaussian splatting. So it's a technique that allows the technique to reconstruct 3D animation with just one single view. And in this context, they also do the reconstruction and the tracking. That is a huge improvement comparing to the previous methods. So the idea is we have one-to-one consistent tracking from one frame to another frame. Namely, it's maintaining the connectivity and topology of the mesh across time. That is a hard problem during many years, obviously. And then the last paper I'm going to present is the promptable human. So the idea is to use technique like prompting, so like the large language model. So the user can guide the system, the user can guide the generative process, the AI deep learning model by inputting some prompts. And the idea is that in some context like this one, if you have multiple characters, multiple persons interacting in close interaction in the same image, and you try to estimate the overall collection, the crowd in 3D, it can be a difficult task. So the idea is to provide some prompts to the deep learning technique to provide more details, also more information to guide the process and have a more accurate estimation of the reconstruction, not for one character, but for a collection of characters, especially in close interaction. It's a very difficult problem because it's packed with occlusion, and it's difficult to have a full observation of all the details. As a conclusion of my talk, I want to once again restate that all those techniques are not designed to replace artists, but to empower them and enhance the creativity, so the real creative process in the loop. And the idea is, especially with promptable techniques, the idea is to involve human in the loop in the process of the generation. So the objective is to use AI to augment the creativity, to boost the efficiency and productivity, to also explore new forms of arts, also to create tools that can be accessible for non-artist users, and to popularize and democratize this kind of technology. But still, the idea is the artist will remain in control of the content. So the creator is the artist and not the AI tool. I think it's an important thing. And as a conclusion, I would like to give you this question to close my presentation. Is the idea is how can artists and computer scientists can collaborate to develop AI tools to have better creative augmentation without compromising on, let's say, employment, human creativity, or even accessibility of the tool. So I will conclude with this question. And then if you have any interest in collaborating for research proposals or other type of research or scientific project, please contact me. I will be very happy to hear from you. Thank you very much for your attention. And I'm going to stop the screen sharing. Okay.